Okay, so sorry, little technical difficulties, had to restart a little bit, but that's all right. Yeah, so then when it comes to this section over here, just focus on the ideas inside the circle stars. Yeah, those are the more important parts. So anyway, so on to the next question. So indium has a tetragonal unit cell where A is equivalent to 0.495 nanometers and C is equivalent to 0.495 nanometers, respectively. If the atomic packing factor and atomic radius are 0.693 nanometers and 0.1625 nanometers, respectively, determine the amount of atoms in each unit cell. All right, so the first thing we should talk about, oh, whoops, I erased that by accident. Units cell. Good enough for now. Anyway, so a tetragonal unit cell is essentially a unit cell. So it's basically like a oh, that's a very ugly looking tetragonal unit cell. Let's do that one more time. So a tetragonal unit cell looks like a rectangular prism, where A is this side over here, C is this side over here, and B is this side over here. So everything, all the angles are at 9 degrees, like a rectangular prism. And then the side length, was it? The side length of A is not equivalent to the side length of C, which is not equivalent to the side length of B, as we see with the unit cells over here. Wait, no. Sorry, I mislabeled things because I'm a dum-dum. I mislabeled something. Sorry about that. All right. So let me correct myself right there. So, no, redemption time, redemption. So A is equivalent to B. So then those two side lengths are the same. So that means if the A parameter is, what was the value that I had before? It was 0.495 nanometers, and that means B must also be 0.495 nanometers. However, those two angles or those two lengths are not equivalent to C. So then that's the tetragonal unit cell. And let's figure out the amount of atoms we have. So when it comes to the amount of atoms we have, well, we can use the equation for the atomic packing factor. So then the atomic packing factor is equivalent to the volume of is equivalent to the volume of the atoms we have divided by the volume of the unit cell. All right. So then when it comes to that, we can rearrange it so that we have the volume of the atoms we have. So then when it comes to the volume of the atoms we have, so I'll just abbreviate that as VA. That's going to be equivalent to the atomic packing factor multiplied by the volume of unit cell. So then we're given the atomic packing factor to be 0.693. And then the volume of the unit cell, well, luckily for us, it's just a tetragonal unit cell, which is essentially a rectangular prism, which means to figure that out, we just need to take the area of the base, which luckily we know the area because it's just a square. So then that's going to be 0.495 nanometers squared multiplied by the height, which is 0.459 nanometers. I apologize that they're very similar to each other, but it is what it is. So then if we were to go through the math, we get a volume of 0.07227 nanometers cubed. So then this value tells us the total volume of all the atoms present within this tetragonal unit cell. All right. So then now let's figure out what is the total amount of atoms we have. So VA is equivalent to N. N refers to the amount of atoms we have multiplied by the volume of one sphere, because we're assuming the hard sphere model where we can just see these atoms as just, well, actual spheres, right? So then let's rearrange a couple things over here. Yeah, so just rearranging a couple things over here. We get N is equivalent to VA all over, what was it? 4/3 times pi times r cubed. So then if we start plugging things in, sorry, I think you guys can tell I'm like kind of low on energy right now, and I apologize. I wish I could be more energetic, but not today. Perhaps another time. So then we're just going to plug in our VA that we have from over here. So then this which makes a return over here. All over 4/3 times pi multiplied by the atomic radii, which we are given to be 0.1625 nanometers. That's going to be raised to the third power. Got that value from over here. So then if we plug and chug, these nanometers cubes will cancel out, and we get a value of 4 atoms essentially. It's not going to be exactly 4, but it's going to be so close to 4, it's just 4 pretty much. So then that's that. And just to really expand on that idea, and this goes down to the very last slide that we have, 7, the atomic weight of indium is 114 grams per mole. Compute the theoretical density. So then this one is just a matter of just taking the equation and just using it. So the theoretical density is equivalent to the amount of atoms we have multiplied by the atomic weight all over the, was it volume of the unit cell. Sorry, yeah. Sorry, let's just do Avogadro's numbers first. Avogadro's number multiplied by the volume of the unit cell. So then if we plug in our values over there, we get 4 atoms multiplied by the atomic weight of 114.82 grams per mole all over Avogadro's number, if you guys know, is 6.022 times 10 to the 23rd moles per atoms multiplied by the, what was it, the volume. And then when it comes to volumes and all these types of equations, you ideally want to be working in terms of centimeters. So what I'll be doing is that, sorry. Yeah, so then when it comes to this, um, well, we figured out the amount of atoms that we have, 4 atoms. And the only crystal structure that has 4 atoms within one unit cell is the FCC. So this means we have an FCC, tetragonal. So that means we have an FCC tetragonal. So then, if we look inside the equation, the side length of one of the side lengths for FCC is 2 times the atomic radius multiplied by square root of 2. So then what I'm going to do there is just do, sorry, 2 times, what is it, the atomic radii would be, if I were to convert that into, what was it, if I were to convert that into the centimeters, that's going to be 1.625 or 8. Was it 5 or 8? I don't remember. It was 5. 1.625 or sorry, multiplied by 10 to the negative eighth centimeters of square root 2 raised to the third power. All right. So then going there, hold on, actually, I should have checked this one before, but I'm curious if it's the same. 2 times 1.625. Just checking something real quickly. Well, actually, it doesn't really matter because I'm just working in terms of centimeters. So yeah, let's just work in terms of that. Yeah. So then just working in terms of that, if we're to plug in our values, we get a value of 7.88 grams per centimeters cubed as our final answer. Yeah. So then, yeah. So then that would be our theoretical density. But then if you search up the actual density of indium, it's going to be slightly lower or slightly larger. And that's all right because sometimes when it comes to density, for example, due to the amount of pressure that a unit cell or crystal structure might be on, then the density might change. But this is the theoretical density of indium. All right. I think that's pretty much all the questions that I have for practice or as an example. And hopefully it helps you a little bit with the P set. And yeah, good luck. I'll see you guys later.